Hi everyone, my name is Zicheng Wang, a master student at the University of Sydney. Today, I will introduce a paper, Conflict-Based Cross-View Consistency for Semi-Supervised Semantic Segmentation. First, I will give a brief introduction to our work. Current semi-supervised segmentation methods may suffer from a confirmation bias issue, which can be alleviated by the co-training framework. However, the two subnets of the co-training framework may step into a collapse, leading to a degradation of the performance. To tackle the problem, we propose a feature description loss to encourage the subnets to extract distinct features to prevent a collapse. However, this operation may introduce a too strong feature perturbation. To keep the training stable, we further propose a conflict-based pseudo-labeling strategy to enable the subnets to learn more useful information from conflicting but confident predictions. Next, I will introduce the method in detail, and I will start with the background. As we know, deep learning-based segmentation methods rely heavily on pixel-wise annotated datasets, where the annotation is extremely expensive. To tackle the issue, many works have been focusing on semi-supervised semantic segmentation. As compared with annotations, it is easy to collect the raw images. These methods aim at learning a deep segmentation model with a small set of labeled data and a large set of unlabeled data. It is obvious that the key to the research is to fully utilize the unlabeled data to extract useful information, as the number of the unlabeled data is much more than the number of the labeled data. Current semi-supervised segmentation methods can be divided into two main categories. The first category is self-training, which firstly learns a model with labeled data and then generates the labels for the unlabeled data and uses the expanded data to retrain the model. The other one is consistency regularization, which aims at enabling the model to generate consistent predictions by using weakly or strongly perturbed data as inputs. However, the above-mentioned methods will be inevitably influenced by the so-called confirmation bias issue, leading to the degradation of the performance. The confirmation bias problem could be alleviated by the co-training framework, which enables two subnets to reason the inputs from different views. However, during the training process, as the inputs or supervisions of the subnets are similar, the subnets might step into a collapse, also leading to a degradation of the performance. To tackle the issue in this work, we propose a new cross-view consistency method to prevent the two subnets from collapsing into each other. In particular, we introduce a new feature discrepancy loss to minimize the cosine similarity between the features extracted by different subnets. Moreover, we further use a non-linear mapping layer to map the features extracted by one subnet to another feature space. In this way, we can encourage the subnets to learn distinct features. Then, we apply a classic cross-pseudo-labeling strategy to transfer the knowledge learned from one subnet to another. We can see from the figures that the cosine similarity between features extracted by two subnets of the traditional cross-consistency regularization method, which we call the CCR method, keeps a high level, while the cosine similarity between features extracted by two subnets of our cross-view consistency method, which we call the CVC method, keeps a low level, which is near zero, indicating that our CVC method can reduce the collapse situation. Moreover, we can also infer from the figures that the CCR method will generate more confident predictions, but the accuracy of the predictions keeps a low level, while our CVC method will generate less confident predictions, but most of the predictions are correct, indicating that our CVC method can efficiently overcome the confirmation bias issue. However, the feature discrepancy loss might introduce a too strong feature perturbation, and the subnets might learn little useful information, and the training will be unstable. To tackle the problem, we further propose a conflict-based pseudo-labeling method, where we encourage pseudo-labels generated by the conflicting but confident predictions of a subnet to have stronger supervision for the prediction of the other one, to enforce the two subnets to make consistent predictions. Here I will give some definitions. When predictions of a subnet are inconsistent, we consider the predictions to be conflicting. And when the prediction score of a prediction is higher than a predefined threshold, we consider the prediction to be confident. We can infer from the figures that, with the training process, our CPL method will encourage the subnets to generate consistent and reliable predictions, like the rear wheel of the bicycle. Experiments and benchmark datasets have validated the effectiveness of the method, our CCVC method achieves a new sort of performance. Moreover, it can be inferred from the qualitative results that our CCVC method can easily recognize those hard-to-distinguish pixels, like the rear wheel of the track bike and even some small objects. Okay, that's all. Thank you for listening.